Okay, so discussing for this week, we will be doing inverse trig functions. Sydney? Inverse trig functions. These are relatively short sections. We'll actually go over both of them today as much as we can, and the homework will be due likely on Thursday with a test over chapter 5 on Trig.
I'm sorry.
We're letting Michael rub off on you. It's not in a good way. Okay. First.
Are we not going to have like a review?
Yeah, it's all one package, man. You either get a terrible mouth and good legs, knowledge, or you don't get anything.
You know, I rarely know of Einstein using the F word.
Wow.
Or Stephen Hawking, although he was a very weird man.
Oh yeah, Stephen Hawking. He had his wife shaved. Well, I guess it was disabled, but he abused his wife, I think.
He definitely
Yes, he did.
used that one
Yep.
then.
Okay.
He abused his wife.
So first, as a reminder, defining an inverse.
Simply just not.
As a reminder, an inverse is a function whose specific goal is to replace the input and output values of each other. So if normally you plug in 1 and output 3, the inverse function is done the exact opposite, where you input 3 and output 1. It's often written with the following notation, with the x and y simply interchanged. We use inverses quite a bit in mathematics to define other functions. This is because most functions need to have an inverse, and most of the math is associated with it. Example, the idea of squaring a number is very natural and obvious in the real world. The idea of square rooting, the undoing of that operation, is not as natural, not as obvious. So we find an inverse to do that function, and then create a system to do that with. Now today, I'm going to talk specifically about inverse trig functions. So, an inverse trig function is designed specifically to follow through on the idea of a trig function by itself in the opposite order. So a normal trig function, such as sine, you have a y value, and you plug x into the trig function. The big thing to note about that is you typically plug in the angle, and what you output is typically a ratio, defined as for sine, opposite over hypotenuse. What an inverse function will do is designed to do the opposite, flipping those two ideas around. So what an inverse will do, and in this case we refer to it as arcsine, the inverse of sine, what it will do is it will take in the ratio and output the angle. Now, depending on the calculator you use, you may have arcsine in your calculator. A lot of older calculators use arcsine. Some use sine inverse. This is not sine to the negative first power, despite how many people want to believe that. It is sine inverse. Whenever students have trouble with using those two, I just tell them use arcsine instead. Make sure you never forget that. So again, it's designed to work in the exact opposite way. Now, modern day mathematicians use calculators for 99% of this, but before, for a long time, if you wanted to solve an arcsine problem, you worked by going backwards. You solved the sine version of the problem using a triangle or using a definable angle, like on a unit circle, and then you work backwards to find the actual value. Modern day mathematicians, we have computers. We have calculators. We do most of that stuff on the side. Now, that being said, there's a few things to know about an inverse trigonometric function. So let's start with an example. What is the arcsine of 3/5? Now, let's first understand what this question is actually asking us to do, because you don't understand the relationship and you don't understand how it's useful. So in this question, we are being asked, here is the ratio. What is the angle? In other words, this particular question is asking us, if I design a triangle with these properties, what angle will I have created? If I design a triangle whose opposite side is 3, whose hypotenuse is 5, what is that missing angle there in the corner? The arcsine relationship allows us to do that step, to determine that missing value. Now again, computers and calculators do 99% of the work these days. But there are some functional values that we can ignore and do it by hand instead, as long as we have a unit circle. Before I go any farther, this kind of problem is not one that can be done with a unit circle. It has to be done with a calculator or a table of values of some kind. So what we're going to do is we're going to grab a calculator, type this in.
The angle is made, the side is.
Are you on this side?
Yeah,
Well, cool. I don't know.
I know, but I think it's cool.
Boom.
It's 4.
It's 4.
Yeah.
The dagger intervals.
Yeah.
Okay.
I want to take a wild shot.
So,
I can say it's like
If
7.
I find a missing value, we got a calculator out. We calculate in sine inverse. On most modern calculators, they use this version of 3 over 5. You can also just do the decimal version, which is also pretty common to see.
Wait, did you say arc sine is sine to the negative first? Is that what it is?
No.
No. It's not negative first.
Arc sine is sine inverse.
Inverse, yes.
To the negative first is something completely different. They look similar.
Okay.
They are very, very, very different. This does not mean 1 over sine. This is wrong. I cannot stress how wrong this is. Don't do that.
Okay.
Completely wrong. I blame engineers because if you're trying to use a calculator and trying to fit everything on that calculator screen, it is far easier to write this than to write that. I blame them.
They also use 3 as 5, so.
I had done that before. I'm not gonna lie to you.
Oh no.
Or 22 over 7.
I'm going to that field, so it's not. Oh no.
Hey, it's a good approximation.
Wait, what?
Completely valid. So, other problems we can solve with the unit circle.
Yeah. I think very those
I feel like it's not correct.
That isn't correct. You didn't circle.
The answer that I got.
What'd you get?
0.64.
Say again?
0.64. 6.4.
So that would be the radian answer. In trigonometry, which we've not taken yet, we talk about how there's 2 primary ways to discuss angles. Radians and degrees. 36.86 degrees. Now, in calculus, almost everything we do is in radians. So this is the answer I will look for. I have only once seen a problem in my entire career where it was in degrees. And even though the problem was in degrees, the answers were always radians. So even if you see a problem that does talk about some degrees, it's always a radian problem.
So I don't have to worry about switching or calculating degrees.
Leave it in radians forever and ever. Degrees is useless. Stop believing those lies.
Me too.
Okay. That's because some kids don't want to convert. So I put them both on there. Yeah, you gotta memorize the whole thing. I'll tell you what, on that entire unit circle, I only have like 1 corner memorized.
That's all you need.
That's all you need.
You can learn the
What'd you say?
So, these are examples of ones that specifically require a calculator. The vast majority of the problems that you have are ones that require a calculator of some kind. There are a select few that do not. They're usually pretty easy to tell which ones are which because of the ratios you might see. If you have a trig ratio that involves square roots of 2, square roots of 3s, or 1/2, any of those combinations, any of them that you might have seen on the unit circle, it's probably wanting you to do a unit circle version of this problem. The reason being is the unit circle often contains more than one solution because there are more than one solution, whereas your calculator only tells you the first solution. Example. If I was to do something like the cosine, or in this case cosine inverse, of the following ratio. Square root of 3 over 2. Now if you got a calculator, it will generate one of these solutions, which is great. It generates the primary solution, the one either in the first or fourth quadrant, is the most common use. On the other hand, the unit circle tells you that there are A, infinitely many solutions, and B, at least 2 just on the unit circle itself. So, let's remind ourselves some things about the unit circle, for those that may not have seen it for a while. As remind the unit circle. Woohoo! Before I continue, as a reminder about the inverses, what this question is asking me is, what angle produces this triangular relationship. This side of square root of 3 and this side of 2. It's asking for the angle. Remember, the inverses always determine an angle. You plug in a ratio, you get out an angle. So the question is asking me what angle has this specific relationship. Well, there's two of them on the unit circle. As you remember with the unit circle, the x values are your cosine values, the y values are your sine values. So in the unit circle, this would tell me that pi over 6 is one solution to this problem. And if you've got a calculator, that's what it'll tell you. The first solution is pi over 6. But it is not the only solution. And the calculator only stops at 1. So, the other solution, I look at the unit circle, I look for another place where I happen to have a function where I have an output of square root of 3 over 2. In that case, 11 pi over 6, or negative pi over 6, is the other solution. Using coterminal angles to determine the second solution. I can also see that if I have my unit circle memorized, because on the unit circle, the x value of square root of 3 over 2 is right there, 11 pi over 6. So, once again, the idea of the unit circle is very simple. It's designed so that it will tell you very specific values for commonly found angles in design. 30, 45, 60, and their variations in the other quadrants. In your homework tonight, there are some problems that specifically say, do not use a calculator. That should imply to you that it wants you to do this with the unit circle. Now, alternatively, there are other versions of these problems where I can also do them without a calculator using Pythagorean's theorem and the missing sides of the given triangle. These look very different. So, here we go. You can tell because these are usually composite problems where you have more than one function happening at the same time. Unlike with some standard functions, these ones will both involve trig. So let's ask the question, what is the sine of the tangent inverse of 5 over 12? Those of you who have taken the trig class already might remember how a composite function like this works. As with all composite functions, the order of operations is you work inside out. So you will solve this part of the problem first before referencing the second part of the problem, which is the sine portion of the problem. So, just like with the previous problem, I can have the option to design a triangle off of this statement. I have the tangent inverse of 5 over 12. This is the main way to do these kinds of problems. Design a triangle first, because the second piece also asks about that same triangle. But while the first piece tells you, hey, the tangent is this phrase, the second piece asks you, what's the sine of that same specific picture? So in this problem, it generates the following triangle. The tangent is 5 over 12. That means the opposite over the adjacent is 5 over 12. There's theta. There's 5. There's 12. Now the question asks specifically about the sine value of this triangle. Because remember, this statement right here references a triangle, which we've now drawn. Now what this problem is asking you, hey, what is the sine of that triangle's angle? I don't need a calculator to do this. Because to find sine, all I need is opposite of hypotenuse. The thing is, I have to use this trig function's triangle to find that sine value. So, one more time. If I want to determine the tangent inverse of 5 over 12, it gives me that picture, which I could find an angle. I can determine what that value is manually using a calculator. But if I don't have a calculator, there is still a way to find the solution. Because the sine of this triangle just means the opposite of the hypotenuse. I have the opposite. The opposite is 5. If I want to find the hypotenuse, how do we know it's 13? Pythagorean theorem or Pythagorean triple. Woo! So, if I want to know the sine of the tangent inverse of a function, what that means is use the tangent function to build a triangle, and then evaluate the sine of that triangle. We work inside to out. So the tangent inverse builds the triangle, then we investigate the sine of that triangle. So in this example, the sine of the tangent inverse of pi over 12 is simply 5 over 13. Because it represents the sine of this defined triangle. So, if the problem says don't use a calculator, it really means one of two things, depending on how it looks. And these look very different. If it's a standard function, it means it's probably on the unit circle somewhere. If it is a composite, it probably means you can draw a picture easily of this function. Now, a few rare cases that can pop up is if they simplify something. Example, what if I had the following? If I asked you about the tangent of the cosecant inverse of 3. Well, just like before, I can use the inner piece of this function to build a triangle. But I have to figure out how to do that because usually I have a ratio, right? If I'm using an inverse, I have a ratio. I don't have an inverse, I have 3. So I create an inverse. I rewrite this not as 3, but as 3 over 1. So now I do have a ratio. So now I can actually build a triangle out of this. I draw my triangle, put my angle theta, give it my right angle. Now, as a reminder, if you haven't seen cosecant before, cosecant is hypotenuse over opposite. So this means my hypotenuse is 3, my opposite is 1. So if the problem is asking for the tangent of this specific picture, I would need to know the opposite and the adjacent. I have the opposite. So we just need to know what's the adjacent. This is Pythagorean theorem is helpful. So notice how they didn't give me a ratio. I created a ratio that is appropriate algebraically. 3 over 1 is the same as 3, so I didn't verify the problem wrong. Again, I still build a triangle off it and then use that relationship to now solve the actual problem, which deals specifically with tangent. I want to know what tangent is. Tangent is opposite over adjacent. I have the opposite. I now define the adjacent. I go through substitution. In this case, my adjacent, 2 squared 2. So for my problem, the solution to this problem, the tangent of the cosecant inverse of 3 is equal to the opposite, 1, over the adjacent, 2 squared 2. Oh, Stanford kids. I love Stanford. In calculus, this is a fine answer. Don't let them lie to you. It's a fine answer. It's fine. Stop. For some reason, the ACT still makes an archaic use of this stupid simplifying rule. Yeah, I said it. This one? Square 2 over 4.
Can't run around with your rat.
I'm not running around how I want to marry.
Yeah. It's just so stupid.
It actually does help a lot.
Why?
Specifically,
Lander.
if there's a function inside a radical. Because if you want to do a derivative,
Oh, no.
like let's say this was 2 square root of x. One of these is a lot easier to do than the other if it's a derivative. Okay? So, consider the ways. Alright.
I'm going to do ACT and that problem's going to pop up and I'll be like, oh, this is 1 over 2 squared root of 2. And then you go,
And I'll be like, APT's wrong. Sorry.
It's the same.
Okay. Let's look at, so,
It's the same number.
let's define inverses. The first few problems in your homework are just, can you use the inverse, can you use a calculator, that kind of basic stuff.
I'm not going to do
There are now the last pieces of derivative and integration. Theorem 516, Theorem 517.
So this is the last section.
I did not say that.
Integration. Last theorem.
This is the last new way you could integrate or differentiate. Now, we talk in, so the rest of this class, we have a month left. we spent a couple weeks talking about other uses of integration, other uses of derivatives. But other than that, like, there's not much new.
Alright, so I'm kind of a nerd, and I watch math videos, but I think everyone knows that. What is the DI method? Is that just something later
Say again?
in DI method?
I hate that method. It's stupid. I'm sorry. You're going in engineering, right?
Yeah.
You will never use it.
No.
Hate to say it. It's only used if you want to go into math. Like, as a field, like me.
Honestly, I'm on the fence. I don't really know.
Like, I loved my math classes, but literally my teacher looked at me moving into that section and was like, hey, by the way, every other person doesn't have to learn this. And I went, really? Seriously? They were like, yeah, because you only use this for mathematical proofs. I was like, I hate to do it right now.
Maybe I just go through your math degree.
Okay, so, as you remember from Trig, there are 6 inverse functions. Arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. And there's a derivative rule for each one. 1, 2,
Are we gonna use this? Are we gonna learn the new one?
yes.
Okay.
Only the u ones from now on. So, the derivative with respect to x, and whenever I send out your homework here in about 5 minutes or so, they will be in the book as well. They'll also contain a yellow section which has all these. So, the derivative of the arcsine function is equal to u prime over the square root of 1 minus u squared. The derivative of arccosine of u is equal to negative u prime of the square root of 1 minus u squared. You notice that not only are sine and cosine derivatives related to each other, arcsine and arccosine derivatives are related to each other. It's kind of neat. The derivative with respect to x of the tangent function, so arctangent of u.
What did it mean? Respect to you?
No.
Oh wait,
If
never
it was
mind.
respect to u, there wouldn't be a u prime on the top.
Never mind, I got it. I'm kind of.
Okay. Arctangent is u prime over 1 plus u squared. No square roots, and it's a plus sign instead.
See, I remember that do well on the AP test, but I barely know my unit circle, and I don't think I'm gonna do well.
Just praying for it the night before. And then
That sounds like a
right
bad
down the-
idea. I'm gonna get a good, decent amount of sleep the night before.
Who needs sleep?
And the
Me.
morning before that, just make sure you have at least 1/4 of that memorized. Finish the rest of it. Write that down.
Okay.
Yeah, I probably will.
3 more. Now, these are out of order because as we go farther down the list, these get more and more difficult. So, and most people do show them out of order. I don't know why. Personally, if they're all, just derivatives, then you can learn whatever order you want. But for some reason, they decided to go out of order. They do arctangent next, or arccotangent, which is, negative u prime.
You went up too slow.
Cheater.
Sitting.
Cheater.
Okay. Arc cosecant and arcsecant. Arc cosecant is negative u prime. And then u prime. Feel free to double check your cheat sheet. This all should be correct. Yeah. You notice this is not a list that I have memorized. I don't have it memorized. Whenever I took the AP exam, I flash memorized them right beforehand, wrote them all down. Mainly because they're all pretty similar. I can get kind of annoying. So, these are derivatives. And this gives us our full list.
What do you mean?
Now,
Like, oh, okay, fine.
like right before I stared at them for 5 minutes and then wrote them all down as soon as I got tests. In a textbook, and what I'm sending out to you guys tonight, there is this nice, neat little page inside of it, which contains a summary of all the integration or all the derivative rules. It's also all the ones that are on your cheat sheet, but these are all written in new form, which is pretty nice. If you want to print something out of you study this little table, very nice to have. Now, theorem 517 is much shorter. This is because when it comes to integration, the list of possible integrals is actually very small because of some of these pieces in here that have troubles. So, by comparison, there are 6 different derivatives you can have, but there's only 3 integrals. Here we go. Theorem 517. Am I clean to scroll down a little bit? Let's go at least go tangent right there. Okay. So, theorem 517. Number 1. The integral of du over square root of a squared minus u squared is equal to arc sine of u over a plus c. Now, there is not one for cosine, specifically because if there was a negative in this problem, you could do a u substitution and move to the outside, and then it would just be a sine problem again. This is mainly because sine and cosine are intrinsically linked by their periods. You can always modify sine to become cosine, you can always modify cosine to become sine. And so we don't need to integrate both. Everything integrates into sine, and if you wanted to, you could convert it into cosine. Second version, similar with secant and cosecant. So, there is only one. It is the secant rule. It states the integral of du over u square root of u squared minus a squared is equal to 1 over a times arcsecant of the absolute value of u over a plus c. And similarly, how there's a relationship between tangent and cotangent. Therefore, with the integration, we only need to know one of them, because if we need the other, we can always convert it. Number 3, the integral of u over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. So again, the list is half as long because it's so easy to convert between them on the other side. We can convert secant to cosecant, convert tangent to cotangent, we can convert sine to cosine. There's no reason to worry about it. And this concludes our list of the integration rules you need to have. These are considered, as everything we've talked about so far, the natural log integrations, the exponential function integrations, the inverse trig function relations, the basic integration rules like the subdifference rule, the power rule. All those rules are considered a big list called the basic integration rules.
The basic?
Oh yeah, there's more. If you go farther in math, you'll learn about more of them. Because many of them are just very specific subcases. Like, oh, here's how you integrate a function that specifically looks like this. And it's like, oh, I'll use this once in my entire life. Cool.
That's what Google is for.
Exactly. Now, also in the thing I will be sending out to you, no, I'm sending out both homework assignments, is this page. It is a summary of every integration rule written in U form, which is very nice. Now, the next 2 days, Tuesday and Wednesday, we're going to focus primarily on the second section, because the first section with the derivative rules it's not that bad, as long as you did the substitution section. It's not that bad. I will answer questions about it on Wednesday, but I won't do a lot of examples in class. We'll do like 2 or 3. Now, what we will spend time doing is the integration rules, because there's some unique things that can pop up and pop up fairly often. Common things like U substitution happen a lot here, but also, what if it's not quite in this form? There is a way to get it in that form using some algebraic techniques like completing the square. What? Completing the square? Yep, the big comeback right here, right now.
Sorry.
You do it on Tuesday.
B over 2 squared or something?
Say what?
B over 2 squared, is that part of it? Add B over
Yes.
2 squared. I think I know that.
How many questions are like this on the AP? That's like roughly. Like one?
Next Monday, after we take this exam, I will actually sit down and show you what we know about the AP approach.
Oh, okay.
It gives a percentile breakdown of what every section is, what categories of each section there are, like how many come from the limit section, how many come from derivative rules, how many come from applications of derivatives, use the first and second derivative test, how many come from integration rules, how many come from these rules. Like, you get to see the percentages as they're defined every single year. So you'll know that question.
Okay.
What do most people that take your class get on the AP test? 1 or 2?
Usually I have about 2. I will tell you this, the AP exam is a devil. I know people who have become engineers, who have become mathematicians, but you did not do well on exam. I do not feel that exam measures how well you learn calculus. Because where is the science? Depending on the school you go to, what we're covering right now, this is actually Calc 2. Depending on the school you go to. If you go to Crowder, Calc 1 stops after derivatives. Calc 2 is just integration. Whereas if you go to Rolla, this is why it's such an annoying thing. If you go to somebody like Rolla or Zoo or you go to A, Calc 1 is both. Calc 2 is sequences and series. So in Crowder only has 4 calc classes. Calc 1, Calc 2, Calc 3, and Calc 4. And you go to like a bigger school, Calc 1 and Calc 2 joined. So the AP exam has to take that into account.
Right.
And assumes you're taking one of those big advanced classes. And so that's why I tell people, like, taking exam is good just because, like, you may get a 5 and get right past it. And if it's the only major math class you're going to take, then you're good to go. Just do it. But if you're going to go to one of those big schools, you probably want to take a class. Even if you get a 5. But you probably still want to take Calc 1. Just because you want to get used to the pace and how they did it. And they're going to focus on different things. When I took Calc S&T, one of the biggest things we did was we spent 3 times as long just doing the trig stuff. Because for S&T, all the trig stuff was the more important stuff. If you're going to be an engineer, the trig parts are more essential than the other parts. Because you're going to be a lot more. Whereas if you take it in like a scientific class, you're not going to do the trig as much. You're going to focus upon the applications of them, so the physics applications. So you're going to take those classes instead. Whereas the AP exam says, we got to pretend you're prepping for all of those. And so I usually look at it and go, I think it's a good thing to take. Whenever I took it, I was number 1 in my Calc class. And I got a 3, and my teacher gave me a birthday. It was like the highest score I ever had. And I was like, no. I took it again after I took Calc 2 and Calc 3 and A Calc and a bunch of other classes, and I got a 5, no problem, because you're forced to use it so much that it becomes the easy part. Going to Algebra 1 in the middle of Calc 1.
Oh, can't wait for that. Or
That's a good time. That's when you really know you've hit the peak of math. Just like, what? You integrate this function? That's step 1 of 12 steps. Alright, easy. Done. Be like,
I wish I could just go straight past it, but I don't